Hello, everyone. So I'm going to talk about time series analysis. So here I give you some introduction, some definitions, applications, and history, classification of the time series analysis methods, and then we go to the parts for methods for statistical deep learning and other stuff. Okay, time series is a sequence of observations taken sequentially in time. This is a definition by Box. And time series analysis deals with techniques for analysis of this type of temporal dependencies. And why time series is important? Because it's massively produced in Internet of Things, in digital healthcare, and smart cities. Time series are collected during the history since 800 BC, where Chinese recorded solar activity. And then later, people started to record the mortality rates. This is perhaps the first time series documented in the history. It dates back to 606. Then in 1887, Waller invented a machine to record the heart speed. And it was the first time that we had this kind of time series that shows the activity of our heart. And then in 1924, we had the first EEG recording, which gives us the new type of time series for monitoring brain activity. Time series also is very famous in finance and also in economics, of course. And people study time series for making money. For instance, this guy in 1970s started to learn about the rules of this time series, when to sell and when to buy in the stock market, and then he could obtain $250 million in 18 years. Another interesting research was done in 1983. Someone studied the newspapers from all over the world, from 74 to 80, and showed that 75% of graphics in the newspaper were actually visualization of time series. Okay, so what is the time series analysis? Time series analysis is two parts. First we want to answer this question: what has happened? So imagine that we have a long time series, and we want to discover interesting patterns, like unusual behavior, kind of peaks like this. For instance, in Euro 2020 final game between England and Italy, England experienced one of the biggest electricity demand shock in their power supply. We also want to detect repeated patterns, like this kind of patterns that are repeating. We have two categories of repeated patterns. One is surprising, that can surprise you. For instance, you may know that after 3 consecutive rainy days, if we have a sunny day, power demand goes down. And then you can interpret it. How? Probably because people get depressed, and then they go out, and then they use less electricity. This is the kind of interesting patterns that you can find from time series. Or you can find known patterns, already known patterns, like or for instance, similar demand increases. We have this kind of patterns as well. And then the next question that we are going to answer in time series analysis is that what will happen? So this is called time series forecasting. So this is kind of that forecast for the next time instance. So, and then it can be long term, how much power we need to supply in the next 3 months, or short term, is there any significant deviation from the expected value? For instance, take the case of England-Italy game. Electricity demand in it was like 500. It was from the previous forecast. Forecasting system said, okay, 500 megawatts we need next hour. And then when final game started, it became 1,800 megawatts. So typically the difference was like 50 megawatts But then, during the game, it became 100, 300 megawatts difference. So something abnormal is going on. This leads to real-time anomaly detection. So if you make a good forecast, you can make real-time anomaly detection system. So there are 4 types of time series data. One is univariate time series, when you are monitoring a single object over time, like you want to monitor sales of water during time in ICA, for instance, supermarket. The second one is multivariate, that you are monitoring 2 objects over time, like Coca-Cola and water. There is a third category where you are monitoring multiple subjects over time. So you are monitoring water sales in 2 supermarkets. Supermarkets here are subjects, subject 1 and subject 2. Then there is a 4th category, which is called multi-way, that you are monitoring multiple objects of multiple subjects over time. And then you have, in this lecture, we are focusing on the first one and the third one, okay? Because this is more famous, more popular, and has more applications. This one is also has lots of applications. We will talk about this. Time series are everywhere. You can find them in weather forecasting, power demand, or sales, anywhere. And there are lots of applications for time series analysis. In finance, you can make forecasting for sales, inventory analysis, make better planning, stock markets, price estimation, temperature prediction, climate change, weather forecasting. In industry, you use it for usage prediction, anomaly detection, and predictive maintenance. In healthcare, you use it for disease outbreak prediction, for instance, prediction of COVID-19 cases, something like that. Insurance benefit prediction, and health monitoring. Okay, now we are going to talk about time series forecasting, the second part, and then we will talk about the time series mining later. Okay, main purpose of the forecasting system is better planning and detect anomalies as fast as possible. These are some examples that you can see in real life. For instance, you can forecast seizure from time series, EEG time series of a patient. You can predict the number of forthcoming COVID-19 cases in Halstead, or closing price of IKEA stock each day, or birth rate at hospitals in Halstead next year or next 2 years. How many products IKEA will sell today in their store? This is another kind of application. The number of passengers that Gothenburg-Halmstad train have tomorrow. This is good for planning. SJ, for instance, is interested in this kind of thing. Unemployment rate in Sweden next year. Power demand in Halmstad next year. And average price of gasoline in Halmstad next week. These are some examples. Or you can make estimation for consumers' price for renewable energy based on forecast of sun and wind. Or you can estimate annual required budget for the government based on various time series. These are the examples in real life. But time series analysis is $1 billion business. So this is a study that was done by Western Electricity Coordination Council in the United States, and they estimated that 20% improvement in time series forecasting accuracy can make like $1 billion money for them. I mean, in saving costs. So let's talk about a little bit about the background. So time series, every time series have some components. One of them is level, is the expected value or baseline that can be average of the time series over time. And this can be with non-constant variance or constant variance. For instance, if you look at the patterns like this, your time series is non-constant variance. And another component is noise, which are small variations that can be because of measurement errors or random noise. These are also another type of components that you have in time series. Another component is trend, where you observe over, upward, and downward movement during long period of time. For instance, growth of passengers due to population growth can be one of these examples. Or for instance, Facebook users is exponentially growing, and they have always trend in their data. Another component is seasonality. When you observe regular pattern of up and down fluctuations. Look at this picture. Before we go, I divide the data into yearly basis. And then look at this. Each of these grid cells are 12 months. And look at this one. These are repeated frequent patterns over time. If you go on, you will see they are similar. This is called seasonality. And lots of business data has seasonality. Another type of component that time series has is outlier. Look at this one, this guy. If you compare this point with its pair in the next 5 years, nothing is abnormal, right? Nothing seems abnormal. It seems fine. But then if you compare with previous year and next year, it seems abnormal, right? So this is called local temporal outlier. You cannot find this kind of outliers with like box plot or any other outlier detection for regular data. You can only detect this kind of outliers with time series methods. There is another type of method, outliers, like this one, that you can detect easily by just taking the maximum value over all values in time series. So these are very easy to detect. But normally, these are the case in time series. Anyway, now let's talk about a stationarity. In time series analysis, they talk a lot about this. What is a stationarity assumption? This is the main assumption of many statistical methods. That means that in a stationary time series, you are allowed only to have level and noise. Very bad news, right? Because lots of real-life time series have all of these components. So you're not allowed to have this kind of thing if you want to use a statistical method. But don't worry. Researchers have provided solutions for you can be able to use statistical methods even they have this kind of components. Okay? But there is 4 methods that you can check the stationarity of your time series. For instance, this one is air passengers. Is non-stationary data, and this one is a stationary because it always goes like this over the average. So now we have 4 methods to you check your time series before starting your analysis. One is that you check what visual inspection if you find this kind of thing, pattern, where the variance over mean changes over time. This is non-constant variance. Or if you see that the mean of the time series over time is changing, going upward or going downward, or you find this kind of repeated frequent patterns. Another approach is seasonal trend decomposition. Seasonal trend decomposition decompose your time series to trend and seasonal components, where you clearly now see your frequent patterns, seasonal patterns, and your trend. And then you can do it with 6 lines of code in Python. It's very useful. And then third approach is that you compute some statistics at random partitions, and then you compare that statistics. If the mean of this partition is different from mean of that partition, that means that you have a non-stationary time series. There are some statistical tests that gives you the results as easy as possible. So you don't need to be worried about, I don't know that this looks like seasonal or it's not. So there are some tests. And with 5 lines of code, you can do this test on your time series. So you see here, you see that we read the airline passenger data that in the first slide you see. And then this is the augmented Dickey-Fuller test that gives you a p-value as a result. If p-value is greater than threshold, which alpha in statistics is like 5% or 1%, then we cannot reject the null hypothesis. Null hypothesis that it looks non-stationary. So we cannot reject this hypothesis, so then we conclude that this is a non-stationary time series. Very easy. We can also fix the non-constant variances with some methods. For instance, logarithmic transformation, a square root transformation, or Box-Cox transformation, which is a combination of these both. Let's take a look at some of these examples. This is the air passenger data, and this is the code that we write for log transformation, S-square transformation, and Box-Cox transformation. And look at this, the results. As you can see here, the variance was varying over time, but after Box-Cox transformation, the variance becomes constant. Or you can remove the trend by differencing. I will explain differencing later when I'm explaining Arima. But the idea is that you just make a first order differencing or second order differencing, and this you can implement this with 5 lines of code in Python that transform this time series, your air passenger data to this data. And as you can see, you have removed your trend. Now your time series doesn't have any trend. You can combine both. You can remove non-constant trend variance and also remove the trend. So it means that you apply Box-Cox transform, and then you make differencing, and then your time series becomes like this. This is a little bit better than the first one. For a statistical method, this is very difficult to deal with this type of time series than this one. Okay, now you start, after you study the background, you start with the statistical models for time series forecasting. The first one is exponential smoothing. This method was invented by Brown in 1956, but you don't believe it. It is still a state of the art. In many competitions, in many businesses, still they are using this strong and powerful method. And it has a very simple logic. It says that prediction is a weighted linear sum of recent past observations or lags. And weights decline exponentially while keeping little record of past. So general formulation of this exponential smoothing is like that. This is the forecast. From now on, I always show forecast with blue color. I show the coefficients or weights with the red color, and I show the observed value with green color. So as you can see, it says that forecast is equal to W multiplied by xt plus 1 minus W multiplied by y sub t minus 1. And W is a smoothing factor. Let's see an example. Imagine that we have a time series of 5 time instants. We put this in the table, like this one. And now we start with the first one. Okay? At the first one, we still don't do anything. So we put our estimate equal to the observation and go to the next one. So at the next time instance, we compute y2 as, according to this equation, we put this there and we compute it here equal to 4.4, right? If you put these values inside this equation, you obtain these values. So this becomes the forecast for next time instance. And then we go to the next one, we compute the same, we put the observation inside this with the coefficients and make an estimation, new estimation. This becomes the forecast for the next time instance. We do the same at t equal to 4, we obtain new estimation. And finally, this becomes the output of exponential smoothing. And look at this one. This was the original time series, and it's converted to this. So it becomes more smooth. For instance, look at this 7. When time series went from 3 to 7, the model said, no, we should not expect 7. We should expect a value like 4. So it's a smooth the time series. So our forecast for the next time instant, according to this table, is 4.2. Very easy, and very powerful method. Other researchers extended this method for a smoothing for both trend and level, which is called double exponential smoothing, which is invented by Holt in 1 year later, and then triple exponential smoothing by Holt-Winter 3 years later, which do the smoothing for both trend, seasonality, and level. You can do this by Python with few lines of code. So here this is the basic package you need, the stat model TSA. So this is the first exponential smoothing, this is the double, and this is the triple. And then look at the results. So this is the air passenger time series. And the blue one is the smooth time series. And look at this one. Simple exponential smoothing is not very well fitted to the data because it doesn't model the trend and seasonality. Double exponential smoothing accounts for level and trend, works a little better. But look at the triple exponential smoothing where it takes into account the level, trend, and seasonality. It seems perfect, isn't it? Okay. So then let's go to autoregressive model. Autoregressive model predicts future values based on past values. Very simple idea. General formulation is that forecast is equal to phi0 plus phi1 x sub t minus 1 plus phi2, sorry, this should be phi2 x sub t minus 2, and go for until we reach the lag number. So autoregressive with 2 lags, or R2, is simply like that. Forecast is equal to phi0 plus phi1 x sub t minus 1 plus phi2 x sub t minus 2. Let's see an example. Let's simulate this data with this package and this function, Arma process. We can simulate this type of time series. And then we generate this simulated data. 100 time series with the size of 100. Now let's write this equation and then put each of these data items inside this formulation. So we start with the last data item here. We put it as a forecast. And then previous time instance as the observed values. And then here, again, we go for previous time instance. This is we put as a forecast, and these 2 previous points as an observation. If we write this forever, we reach to this point. We no longer have data points to put this in this equation. So we have 98 equations and 3 coefficients. So it's a easy problem with linear least squares. We can solve this problem easily. And also Python does it for you very easily too. Autoregressive function from a stats model TSA can do this. And then finally, Python gives you these 3 phi values. What that means? That means that if now we put these phi values inside this one, we obtain this equation. This is the equation that we can make forecast with this equation now. Then we have moving average model. General formulation is y sub t is equal to mu. Mu is the average, which should be estimated by the model, plus theta sub 1 e sub t minus 1 plus theta 2 e t minus 2 plus until phi q e t minus q, where e is the estimation error. It is a bit different from the autoregressive model, where xt is observed, green color, yt minus 1 is the previous forecast, blue color. Let's see an example. So let's say that we are making a moving average with 1 lag. What means? Means that we have only et minus 1. So it becomes this equation. Now let's fit this data with the moving average model. So we write the model, and we have a time series with 5 time instance. from the initial estimates, if we compute the average of this time series, it becomes like 12.8. And theta 1 is 0.2, right? We are starting with a random coefficient, but the model should figure it out. We start with a random one. Now we put our time series in this table like exponential smoothing. So we compute, based on this equation, we put mu, theta 1, and 14, which is the observation, minus non-available data, which we put 0 here in this, and it becomes 12.8. So at this point, we make no forecast because we don't have a previous time instance. Then we go to the next point. It's 15. We put it in the same equation, but this time we have estimation from previous time instance, which is 12.8. So we put it here. So it becomes 13.24. Now the forecast for this time instance is the estimation from the previous time instance. So this one is forecast. Let's go to the next one. We compute again, put the previous estimate in the formulation, we obtain new value. And then we make forecast for the next time instance until we reach to the end of time series. So our forecast for the next time instance, t equal to 6 is 12.89. So it means that the next time instance should be 12.89. And see how the time series has been changed, transformed from these values to these values. So kind of it smooths the gain. So as you can see, the values varies over the mean. What was the mean? Was 12.8. Look at these values. They are not very much different from the mean. So moving average tries to keep the values as much as possible close to the average. This is what moving average does. Solutions is not very straightforward like autoregressive model because we don't have the lag errors. They are not observable. So this should be solved with more complicated approaches like maximum likelihood estimations invented by Box-Jenkins. I will talk about this later, or nonlinear least squares. Let's have some fun. You can run this code on your computer later. This is the data I got from the Swedish weather sources. This is the average of monthly temperature in Halstead during the last 3 years. And I fitted a moving average model to this data. Moving average with 5 lags. It means that I take last 5 of errors. And look at my forecast. In the first time it says it's very close, but then it goes very bad. This is the drawback of moving average, or basically a statistical model. They are very good at making one step ahead, not anymore, because they don't have more observations. So they just propagate errors to the next time. You can take the data from this link. You will have this link later, and then put this in this code and rerun this experiment, and you observe yourself how moving average works in practice. So now we arrive to the point that is interesting. Autoregressive moving average, Arma model, are the most famous model ever in the time series. So it is. Do you know this guy? Anyone knows him? Wolf. It was a Swedish Norwegian mathematician that invented this. So he believed that any stationary time series can be combination of 2 time series, one deterministic and one stochastic. So actually, the first one is our model, and the second one is moving average. So if you marry our model with the moving average model, you make Arma model. Unfortunately, Wolf could not draw equations for maximum likelihood estimation, and later Borst and Jenkins in 1970, like 32 years later, could do it, and then make this model a practical model. So this is an example of Arma model where we have 3 lags for autoregressive and 2 lags for the moving average. So you can expect from this model something like that. So this is the forecast, a constant value, a coefficient for the autoregressive model, and coefficients for the moving average models. So again, this is can be fitted with the maximum likelihood estimation. And then we have Arima. Then, you know, if you go to work as a data scientist in the industry, everyone talks about Arima. What is Arima? Arima is nothing more than doing a differencing over Arma. So it means that we do differencing of the data before we fit it into the Arma model. What is differencing now? Let's see an example. You see that we have a time series of 4 times the 2, 5, 8, 9. So we start with the last time point, 9, and then we compute the difference, 9 minus 8, and then 8 minus 5, and then 5 minus 2 becomes 3, 4, 1, right? Second order differencing is that you take this output of the first order differencing, and then again do the same procedure. 1 minus 4, 4 minus 3 becomes 1 minus 3. So you have done second order differencing. This is the only difference of Arima model with the Arma model. So instead of original raw data, you just compute the first or second order differencing. And in practice, you don't go beyond the second order differencing. But why differencing? Look at this example. We had average temperature in 1800 like this. In June and July and August, we have 16 average, 15 and 13. And now in temperature in 2020, it's 20, 19 and 17. These are different values, right? Different values. If you go into the time series, they are in top and this one is in the bottom. But if you compute the differences with the first order differencing, they become equal. So it doesn't matter which year you are. Always the difference between June, July, and August is the same. This is the idea of differencing. So look at this time series. If you make differencing, then you don't have the trend anymore. And this is how Arima model takes into account the trend. Okay, now there is another version of Arima that wins in many competitions, in many time series competitions, and in the industry. It's very, very popular because not only taking into account the trend, but also the seasonality. So F Arima model is a little bit more complicated. Instead of PDQ, which were lags for autoregressive moving average and differencing order of differencing, it takes also 3 more values with the uppercase letters, PDQ, for the seasonal component. And the M is the seasonal lag. For instance, for this data of the airline passengers, the CM is equal to 12 because we already know that every 12 months, a pattern repeated itself. If you see, this is the example of Is Arima. It contains a differencing for the raw data, differencing for the seasonal lags, and this is the code that you should take home, this code, because this is you can do Is Arima, you can do Arima, you can do R, you can do moving average, and you don't need to be worried about how to set P, Q, D, or this kind of hyperparameters. It does it automatically. This function, auto Arima from PMD Arima package, you just set the maximum number of P, and with grid search, it finds the optimized hyperparameters for your model. So look at the predictions with Is Arima for the air passenger data. Look how accurate it is. Because it takes into account trend, seasonality, autoregressive, everything, noise. So this is a comparison of the assumption of this method. So as you can see, Is Arima doesn't assume that the data should be seasonality free. It doesn't assume that it should be constant mean, and it doesn't. But it assumes that the data should have a constant variance. So Box-Cox transform still is necessary. And then model selection you can do with the two methods. One is visualization with ACF plot and PACF plot, or hyperparameter tuning with grid search, where you test different models ordered exhaustively, like Autoregressive. A model is a good model when it is more accurate and less complex. So the model should be more accurate. When we're fitting the data, it has less error. So we test different parameters, P and Q. We start with P equal to 2, Q equal to 3, and D equal to 1, and we see how is the error. And then we test another setting. And then we have a list of errors, and then we have a list of number of coefficients. For instance, a model that have P equal to 2 is less complex than the model that has 10 coefficients. So finally, we find the trade-off between accuracy and less complexity. This is how autoregressive works. So ACF plot describes the autocorrelation between an observation and another observation at period time step that includes the direct and indirect dependence information. So how to calculate ACF plot? Very easy. So you start from lag 1 to maximum number of lags, and then you compute the just Spearman correlation coefficients of xt and x lag n. Let's look at an example. So let's say that we have this time series 1, 2, 3, 8. So first, we start from this point, remove 2 first, because we are looking for lag 2, so we don't have sufficient data, because for computation correlation, we should have the same equal number of instances. So we make a copy of this time series with one shift toward the left. So let's say here, we move it 1 to the left. So it becomes x lag 1. And then if we move 2 towards the left, it becomes this. Now we compute the correlation between this one and this one, this one and this one. This becomes the ACF plot. Very easy. So ACF plot is like this. And this blue area says that any value inside this doesn't account. So you can consider that 0. So what means? It means that only 4 lags are important. PACF plot, or partial autocorrelation, is a bit more complicated. If you read it in the article again, you find it very complicated, but it is not. It's actually very easy. Describes the direct relationship between an observation and its lag. How to calculate partial autocorrelation? We just need to fit a linear regression model with xt equal to phi0 plus phi1 x minus t1 and etc. And then you remove the coefficients for the lag except your desired lag. So if your desired lag is 10, you just keep the phi for the 10. Okay? So here you see that only 2 lags are important. So, and then how you interpret this plot, based on interpretation of this result, you can find out which models are good for you. If ACF plot tails off and PACF plot tails off, this shows that this is the Arma model. Your time series follows Arma model. If ACF cuts off after Q lags, like this, and tails off in PACF plot, this means that you have a moving average model. If ACF plot tails off and PACF plot cuts off after P lags, then you have an R model. So, and this is the code you don't need to write it yourself. So this is a plot ACF, very simple function in this stats model package. Advantage and disadvantage of a statistical model. The advantage is that they are simple, transparent, and accurate. They are a state-of-the-art performance for small data sets, better than deep learning, for instance, or machine learning. They have, but however, they come with some drawbacks. And one of them is that you don't get better results if you add more data. Doesn't make any difference. And they are not able to capture nonlinear dynamics in the time series, like what deep learning does. And the other problem is that they just make one step ahead forecast. The rest after that is less accurate. It is still possible to make forecast for next 5 instances, but from after one becomes less accurate. Now let's talk about state space models. Are you familiar with state space models? Okay, good. So we want to provide a precise estimation of a non-measurable variable. They normally call it hidden variable, but I don't like hidden variable because I think this is a better term for people to understand. Non-measurable variable, and I give you an example in the real world example. Inaccurate measurable variable based on an inaccurate measurable variable, and then when you have a period knowledge about underlying dynamic of the system. This is very important. A statistical method cannot incorporate this kind of knowledge. That is why you need the state space model. There are two famous ones, Kalman Filter and hidden Markov model. Okay, let's see an example. As you may know, Kalman Filter was invented by Kalman in 1960, and then 9 years later, it was used in NASA Apollo 11 mission. Okay, so look at this example. So imagine that we have a radar tracking system, and then we want to compute estimated velocity. We have no direct way to calculate the velocity because we don't have access to the plane. We don't communicate with the enemy, right? So we cannot ask enemy, hey, where are you? They never tell you. So we should estimate their position based on the data that we can have. So we can send a track beam to the target every 5 seconds. So we know that this is not 100 precise because of the radar calibration, beam width, the return echo, lots of things, that this information becomes inaccurate, uncertain. And then we want to estimate a non-measurable variable, which is the velocity. We want to see where this airplane is going. Is going to attach which point? So this never can be measured, but we know something from the dynamic of the system, underlying dynamic of the system. So we know that from physics, we know that velocity is the distance traveled to the delta t. And from this one, if we put this here like this, we can estimate the next position based on the velocity multiplied by delta t. Very easy. Now let's compute this. Let's imagine that we know this initial estimate that this airplane is 30,000 meters away, and its velocity should be like around 50 meters per second. This is not important. You can put anything here, and Kalman Filter later will update it in a realistic way. So at first time 0, we don't have any observation yet. We know that velocity is 50, estimated distance is 30,000. So based on this formula, we say that y1 is equal to 30,000, first initial distance, plus velocity, initial velocity multiplied by 5. So we estimate that next time instance, airplane should be at this distance, right? Now let's go to the time instant 1, here. So now we send the beam, and it returned back. So we observe that the airplane is in this distance. So we compute the difference of this distance with our previous estimate, which is minus 90. Then we estimate the velocity based on this formula by a weighting coefficients, alpha and beta. Alpha is accounts for the correction of estimation error, and for velocity, and beta accounts for the correction of estimated distance. Now if we put this here, initial velocity plus beta 0.1 multiplied by dx minus 2 divided by 5, the estimated velocity becomes 48.2. And based on the same concept, based on this formula, we can estimate the distance with this value. And then we put this in this formula from that we already know. The next position of airplane, we estimate that becomes this. Sorry. So, as you can see, these coefficients, beta, adjust estimation errors. Okay? So, now let's go to the next time instance. We do the same, and we obtain this. So, imagine that instead of 30,265, we had 30,000, which is like 530 meters higher. It's a bit strange. It should not be like that. It seems that it's an error. So let's try that. Let's try put 31,000. And we compute this, and compute this, and compute this estimation. Now take a look at the differences. This is the observed value, 31,000, and this is the estimation by Kalman Filter, 3,578. 422 meters correction of measurement error. This is what Kalman Filter does. It corrects your measurement errors. And then let's put this value inside this to compute the expected velocity. It becomes 105. And let's look at this estimated velocity. Compare these two. Look, we thought the velocity should be 105.1. So it corrected the estimation error by 46 meters per second, right? This is Kalman Filter. Corrects both measurement as estimation errors. So you don't get worried. And that's why they use it in NASA Apollo. Okay? So now hidden Markov model. They are very closely related. So let's think that we don't have these two equations anymore. So we don't know anything about physics. Let's forget physics. And then let's think that our airplane has only three discrete velocity. It can have velocity 45, 50, or 55. No other values. So discrete values. And let's assume that the chance of having 50 is 80%. Now, this is the velocity. It means that it is a chance. It is a higher chance if from velocity 50 we go to velocity 50. And it is less probable that we decrease the velocity. From 50 we go to 45. This is the period knowledge. And then now let's think that we have another table that says that if we have velocity 45, what is the distance traveled? It is high probable that distance traveled is 225, right? Let's assume that we have this data. I will tell you how you obtain this data, but for now, assume that we have this data. Okay, and then imagine that we have it like the previous example. We know the first time instance location of the airplane. Initial estimate. Okay, so estimated velocity is 50. Why? Because it's more probable. Estimated distance that we already have an initial idea. Okay, now we send a beam to the airplane. It comes back, and we observe. This is 30,225. So what is the dx? Dx becomes this one minus estimate, becomes 225. Now we want to estimate the velocity. What is the velocity of airplane? Now let's compute it with the by theory. Okay? So how is it? So we know that velocity can be either 45 or 50 or 55, right? It cannot be 60 or other value. So we compute the probability of these three, each of these three. Let's say we test for V1 equal to 41 or 50 or 55, right? And then you notice that the probability for 50 is higher than the other two. So we predict that the next estimated velocity should be 50. Now let's estimate the next distance. We do the same. Distance can be from one of these 5 states, 200, 225 to 300. Let's compute the probability for each of these 5, and then compute the highest probability is because 250. So now we add this with 250, and this is our next estimate. So the airplane should be at this position. Now let's talk about what are these in the hidden Markov model formulation. This is initial estimate. This is transition matrix. This is emission matrix. This is observed sequence. And this is forecast. And the method that you use for computing this probability is maximum likelihood estimation. This is also prior knowledge about the system. So what is the difference of hidden Markov model and Kalman filter now? So as you can see, in Kalman filter, we have some formula from physics, from chemistry, from disease outbreak, anything, any formula can be here. But in hidden Markov model, we have some probabilities. We don't have any formula. And then how we obtain these matrices? So this is an example. Imagine that you're in an airplane, and you put this, and you block all the velocities, and then your airplane shows only 3 values, 45, 50, and 55. And then for GPS, you compute the distance traveled every 5 seconds. So imagine that at t equal to 1, your speed was 50, at t equal to 5, your speed was 45. And then from GPS, you have position as well, the distance traveled. So how we compute the initial probabilities? So we just count the number of 50 in this table. It's 7. Divided by number of samples, it gives you the idea of the probability of having 50. Now, transition matrix. We look at the combinations where always 45 goes after 50. How many times it has happened? 2 times. How many cases we have? 17 cases. So this is the probability of 45 after 50. And then how we can make emission matrix. So we see that after 50, with a speed of 50, we have 250. How many times we observe this? 4 times. 4 times divided by 17. So this is the Python code of this example. Exactly the same example. So you can rerun it yourself. This is the initial probabilities. This is the transition matrix, and this is the emission matrix. And this is your observation. And then this gives you a velocity estimated. Then let's go to deep learning models. Okay? Deep learning models are usually useful when you have big data, large data sets, and you don't have any prior knowledge, you don't know anything about seasonality, you don't know anything. You just want computer does everything for you. So how it works? The feed-forward neural network, first you need to transform your time series in this way. So you take these 3 values as the observation and put this one as a target. Then go a sliding window. This second go here, and then 50 goes here. And then you transform your time series like this, and then the rest is like feature matrix in machine learning, right? The rest is similar. So this is the code that you can use for making predictions of this example. Exactly same example that I showed you, this time series. Now let's go to see what's the problem. So the problem is that neural network, the regular neural network, it doesn't matter where order of sequence is not modeled. So if you shift the order of this data, your result doesn't change. And in some applications, this is important because it is an increasing order, and this is a decreasing order. These are totally different concepts. And neural network cannot model this, the regular one. Now let's see how convolutional neural network handles this a little bit better. So it uses a convolutional layer, like here, this example, and a pooling layer, and the rest is like other deep learning. So this actually filters, extract potential features from your time series, and this pooling is downsampled it. So let's see an example. Let's say that we have 6 filters with window size of 2. So we generate random numbers of size 2, and then we make a dot product of this filter with our examples to find their similarities. We want to find the similarity of this filter with this one. So multiply 0.5 by 10, 0.2 by 20, and then again with the next example. With this next, if we move the sliding window to the right, because we have two filter of size 2, then so we have only two conditions. So 0.5 multiplied by 20, 0.2 multiplied by 30 becomes 916. Then we go to the next filter, do the same computation, and we obtain this. If we continue this for other filters, we obtain these values. Then max pooling says that take the maximum value. Okay, take the maximum value of this is 16, take the maximum value of this is 14, and then here. So this is a new representation of your data. So this data, 10, 20, 30, was converted to this one, right? So this is how you can do this, the same example in Python. And then what's the difference? So now if you change the order of time series, the results would change, because the filter moves over the sliding window with the order. So the order is somehow modeled that is not perfect, but is good, better than feed-forward model. So in the applications, when the sequence of order is very important, you need to go to the next model, next architecture, recurrent neural network. But if the sequence of order is not that important, like processes, instance or data, and this kind of thing, then still you can use a feed-forward or one-dimensional convolutional neural network. So this is the basic architecture of recurrent neural network, where this is the input observation and this is the output, and the output of this hidden layer goes itself to it again and again. So it contains this information from its time instance and the previous information from the previous time instance. Let's see an example. So let's put 10, 20, 30 in this. So at the first time instance, we don't have any previous value, so we just take we should put two weights, weight W1 and W2. Our input is 10. We don't have any state. So the weighted sum becomes 0.5 multiplied by 10 equals to 5. So if we apply ReLU, activation function, on this becomes 5. Now in the next time instance, we have 20. We put 20, and we compute the weighted sum. 0.5 multiplied by 20, the observation, plus 0.2 multiplied by 5, which is activation function output of the previous time instance. Look how recurrent neural network, you can take into account the order of the sequence. It takes data also from the previous time instance. So, and then we do the same procedure, and this is the output. So you need to estimate 3 weights. This weight, and this weight, which are constant during when you move through those data. So then you go to the next example, but still you take something from previous time instance. And this is how it works actually. So you see, they are combined go to the activation functions and then output. So, but simple recurrent neural network cannot remember past the data due to vanishing gradient problem. So if you want better model that can remember past better than recurrent neural network, then you should go to LSTM or GRU. So this is a Python code for LSTM. You can run this example and then see how it works. So what is the advantage of and disadvantages of neural network? So the advantage is that they are robust to noise and missing values. They can learn both linear and nonlinear relationship in time series. They have direct support for multi-step and multivariate forecasting, where statistical models doesn't have this. There is no requirement for stationarity. You don't need to be worried about, my time series has seasonality or not. No, not anymore. There is no need to develop the art and skills of picking parameters like Arima models, or there is no need to develop a hypothesis about dynamic of the system. So like a state space model, I don't care what is the velocity, what is the formulation for this, or I don't care. The neural network already have figured it out. So what is the disadvantages of this? So it has a problem with trends. Your data should not have trends. And classical methods, like statistical models, in the practical applications, they have been shown that are better than deep learning models, especially for short-term forecasting. And they are not very well developed, like neural networks for image or video or this kind of things. So you find less guidance and rule of thumb for selecting and training architecture. So this is the bad news. This is a paper published in 2018, I think. They did experiments with all the statistical methods and deep learning methods, and then they find out that, okay, exponential smoothing is the best one, comparing deep learning and other stuff. So that means that you still need a statistical methods to deal with real problems. There are other methods as well. If you read the literature of time series, you find Prophet. It's a Facebook designed time series models specifically designed for business data and their own data, actually. What is the motivation of this method was that Facebook it deals with human data, and human data is highly seasonal, and their data is highly with high trends because their number of users is exponentially growing. So they need their own time series models to make predictions and forecasting. For instance, they have users from Muslim countries, they have users from Western countries, and the calendar is different in Islamic countries and Western countries. So they take into account this kind of irregular calendars and also periodic changes, weekly, yearly, based on the basis of different bases. So the main idea is that instead of complicated statistical models, they use a curve fitting method and also put the analyst in the loop. This is the basic idea. Now let's go to time series mining. Now we want to understand what has happened in the time series. Now we could predict the future with the previous slide. Now we want to see what has happened in the time series. So let's take this example. You, by your eyes, look at this plot and you understand something. Oh, there are 3 peaks. It's increasing, right? Summary of this statistic. Then let's go to this one. 1, 2, 3, 4, 5, 6, 6. How many peaks I have? How many go on down? I don't know. Well, let's go to 1,000. Oh my God. How many peaks I have now? How is this spread? Why is it going down? Why is it going down? So you don't understand anything. After it goes to 10,000, nothing. After you go to 1 million, 0. You don't understand anything. You plot the time series and say, okay. So this is the problem. With the size of time series, it's more difficult to our brain to find patterns. This is why we need data mining. So let's look at this example. This is an example of Motifs, where we have repeated values in time series. For instance, if you compute the Motifs, you find these 2 regular patterns. If you look at them, oh my God, so similar, right? Huh? So, but this is a very basic Motifs. Normally, the Motifs in real practices are very far from each other. One is this and one is the next year. It can be fun, finding Motifs. Look at this signal of this sound signal of this zebra finch. And then we apply Motif discovery. We find these 2 Motifs. Huh? So what does that mean? Probably these 2 means that good morning, and then this one means nice day. We can learn the language of animals by finding Motifs. So this is a real-world application of Motifs. So, and also rare patterns. For instance, this one is a rare pattern. So, for instance, in ECG heartbeat data, they found 2 strange discords that they are related to some disease. So let's see how we can find now this kind of patterns. So we start with the time series. We put a current window, this one, and then we move this window over time for the all time instance. And then we find that The closest match of this window is this window. And the distance is this one. Let's do it for the next one. Let's go to the window 69. We move over a sliding window, and then we find that the closest match is this one. And it looks similar, right? Let's try this window. We move a sliding window, and we find this one. This is not similar. So this guy doesn't have any friend in this time series. So let's see. Let's continue. This is the current window. Let's move this window again. And the closest match is neighbor. Let's move again. Let's go to the last time instance. And the closest match is here. And it looks similar, right? Looks similar. So if we continue this for all these sliding windows, we compute the distance. And this is called distance profile. Very easy, right? Distance profile. And with this distance profile, you can't imagine how many problems you can solve. I will show you later. So you continue this current window, and then you obtain this distance profile. This is the distance profile of this time series. So let's take an example of this one. The guy that didn't have any friend. So his friend was here. The closest friend is here. And the distance is 11.94. It's the maximum value in the whole distance profile. So this guy is called discord because his nearest friend is the most farthest. And then look at these guys. These are the motifs because they have the minimum distance profile in the distance profile, minimum value in distance 0.5. So calculating distance profile used to be very expensive before 2016. Before 2016, you could not do it in a large scale. What happened? Because computation of this paved distance takes lots of time. It is n power 2 by m, which m is the size of window. And you need a space of n power 2, which is not possible. Imagine that 1 million time series multiplied by 1 million. In 2016, these researchers published 2 papers in IEEE ICDM conference that they solved this problem. So now, instead of 1,585 years to compute distance profile for a time series of 100 million and in the size of 400, you need only 12 days, which is feasible, right? 100 million time instance. So this is the code. There are packages. You can easily, this is one line of code, np.compute. It is time series and this is a window. You set window size is 150. And then np.discover.motifs gives you the motifs. Very easy. And this code is the same. So we use the ECG heartbeat data, which is available inside this package. Fourier Transform, wavelet, piecewise aggregate approximation, and symbolic aggregate approximation. So it is 4 methods. Transformation of time series, decomposition of time series to reduce representation, something simpler. Example, the most basic transformation you can make is, for instance, if this is a time series, the transformation, the best transformation is that, okay, the next value is previous value plus 1. Once you have this, you can remove this data. From now on, I know that the next value is always previous value plus 1. This is the very easy transformation. It can be used for forecasting. It can be used for compressing the original data. This is the idea of transformation. Any series can be expressed as a weighted sum of signs of different frequencies. Look at this time series. You don't believe that this time series is the combination of a simple sine waves. Sine wave of 2 Hz and 7 Hz. If you add this purple and blue, you make this black. So Fourier Transform actually transforms this time series to this frequency domain, where it says that, okay, you have your data, you have 2 sine waves, one is 2 Hz and one is 7 Hz, right? So from this one, you can return back to your original data. So let's forget that. You generate sinus 2 Hz and sinus 7 Hz. This one plus this one becomes this one, right? is like the previous example. This is like exactly like this, more advanced way. So for understanding this time series, I just know that my time is minus 2 plus minus 7. So now I can't make any prediction because sine wave is a predictive function. You can predict the next time instance. You can predict the 20 time instance. And also this one, you can do plot, and then you make an accurate prediction, right? So this is the idea of Fourier Transform. You can do it in the NumPy FFT function. This is very easy, but you can do it yourself. It's 5 few lines of code. So you multiply a signal with a series of sine waves with different frequencies. You start with a reference frequency of 1 hertz to 100 hertz. And then you make a dot product of this sine waves with your original data. Large amplitude of dot product shows the presence of that frequency. So you will start with h from 1 to 50 and put it in this, generated this, and then make a dot product and then plot. Same products, right? So, but what is the limitation of Fourier transform? The limitation is that, okay, let's make an experiment. In the previous example, we had these two time series added together, right? But let's do another experiment. Let's add these two time series, conconnect them vertically. So it means that this time series, this part is this one, this part is this one, right? Now let's apply Fourier transform. It's the same result, more or less. These are not significant, so these are the same result. So it says that your data has two sine waves, 1, 2 hertz and 1, 7 hertz. What is the problem? We don't know where is my sine 2 hertz and where is my sine 7 hertz. We don't know. Is here, is here, is here, is here, we don't know. This is the idea that motivated wavelets. Why people invented wavelets? Because they were not able to say, with Fourier transform, they were not able, where is my sine wave? So they replaced sine waves with wavelets, which is like this one. But why say wavelets? Because sine wave is not localized in time. It stretches out from minus infinity to plus infinity. But wavelet is localized in time. So it allows to obtain time information in addition to frequency information. This is the basic idea of wavelets. Why wavelet is better than Fourier transform? Because it says, where is my time wave? Look at this example. This is time, this is the scale, and this is frequency. This is the only additional dimension that wavelet has and Fourier transform doesn't have. It says that, okay, where you move the sliding window, the wavelets, and compute the dot product, there is more, we have more wavelets. Where is the presence of this wavelet? For instance, here, the wavelet is not here, but it's here. So you have a peak here, right? This is the basic idea of wavelets. There are lots of them for different purposes and different applications. They're discrete and continuous. We don't go into the details in the signal processing course. If you have, you will study this thing. So this is the code. You need this package, and then you can, as you can see, we applied it to the passenger data, and it fits very well. Okay, now you understand Fourier transform. You understand what is wavelet. So what is peaceful aggregate approximation? So instead of moving this sliding window, let's moving this a simple sliding window. And actually, it's not a sliding window. It's dividing the data into windows. It's not a sliding. So it's like I take this window, compute the average of values inside this window. This is my PAA value. Then go to the window, this window, this window, this window. This is peaceful aggregated. This is used for dimension reduction of time series for large time series databases. And this is the code that you can apply, and that gives you this result. And then we have facts. So this is the basic idea also. It works on the PAA values. It works on the normalized time series values that have a highly Gaussian distribution. So we determine the breakpoints from the statistical tables on these PA values, and then produce the equal size area of the recurrence. Let's give an example. So let's say that we have a time series. This one has a 24-time instance. So if we apply PAA, we have this. This is our PAA. Now, let's say that we want to transform this time series to 3 symbols. Okay? So from the Gaussian distribution, the breakpoint is that minus 0.43 and 0.43. So if we put it here, we can divide the time series values into 3 parts. One is lower than these values, one is between these values, and one is upper than this. So then we go to the divide this data, and then we have cells. We have 12 cells here, 4 by 3. Now we go to see PA values. PA values inside this cell, it becomes A. PA value here goes to cell here, which is C. Then here we go B, and here we go to the A, right? Very simple. So why we do this? So this time series, big time series, 25 times, says now it's transformed to ACBA. It's compressed. So this is the SAX transformation. You can use this code for regenerating this output. Now let's go to time series classification and clustering. So clustering group objects based on similarity of their time series is time series clustering. So you remember this type of data? We have 2 subjects and we have their water cells. So example, clustering patients based on their EEG time series. We have 10 patients and we apply hierarchical clustering. We cut the tree from here, and it turns out that we have 3 clusters, right? And it seems that this patient is weird. Probably he has some disease or something because it doesn't fit the clusters. So this is the idea of time series clustering. How you do this? You have your multi-subject time series here. You use the most popular method for computing pairwise distance in time series is dynamic time warping, because dynamic time warping do you know about dynamic time warping? Because it can find the optimum distance between 2 time series. You can see that it goes which part of this time series gives less distance. Look at this one. So if time series has a little bit shift, but still it's similar, time warping is still considered as a similar time series. So this is the idea of dynamic time warping. It's quite popular. In time series, you don't use equivalent distance. You use dynamic time warping. So keep in this mind. This is the pairwise distance obtained from dynamic, and then we have cluster, right? Easy. Now we have classification, where we are given a time series of multiple subjects, and you're given labels as well. You say that, okay, this water cell is from Ika. This water cell is from Cook. You have labels. So in step 1, you train on this data, and in the step 2, you predict. Machine learning on time series is not like machine learning on feature matrices. Keep in mind, because of this autocorrelation that time series have, and the non-IID assumption that machine learning have. So if you are interested in time series classification, I refer to your timeseriesclassification.com. But this is the state of the art. This is the state of the art method for time series classification. Dynamic time warping plus k nearest neighbors. So this is a code that you can apply on this data set. This is available in this package, in this UCR data set. This is the ECG data, and this is your function that you need. This is the most important: nearest neighbor time series classifier, number of neighbors, and metric dynamic time warping. Time series classification. Another approach, which is very interesting, recently emerged, 2018, is that we extract some features from time series, random features like number of peaks, max, median, some statistics, and this thing, that put them all together, like this package does. TS Fresh ultimately extracts 1,200 features from time series, which are, some of them are irrelevant. But the good point is that machine learning or deep learning can find the relevant features, right? You don't need to be worried about what features are relevant and which are not relevant. So it is a very promising direction in time series classification. You extract features with this package, and then feed it in any time in a machine learning method, okay? Missing value estimation. Any time series in real practice has missing values, and you need to take care of that. There are lots of methods: interpolation, last next observation, moving average, mean, model-based like Kalman Filter, Arima, seasonal decomposition. All of these approaches can be used. Unfortunately, Python is not good. That's why I just, in this case, exceptionally, I put R code because it has a very, very good package for time series missing value estimation. With Python, you have only one function. This is interpolate. So imagine that in error passenger data, we remove time is at 4, and then with this interpolate, we can make prediction. So noise removal, we need. We also have some methods for smoothing, which also can be used for noise removal. For instance, simple average, binning, moving average, and weighting moving average. Normalization, in some applications like time series classification and clustering, you need to normalize your data before feeding it into the model. Or in multivariate time series, when you are measuring different things like temperature and pressure, you definitely need to normalize your data. Otherwise, your model is not valid anymore. This is a code for normalization and standardization. And sometimes you need to resample your data. For instance, here you resample from, for instance, months to day. In here you resample from months to years. So these also, some applications is useful. These are 11 packages for related for time series. Matrix profile, Stumpy for matrix profile, statistical time series models, Arima and Autoregressive, deep learning models, time series classification and clustering, extracting features, spheres, Kalman Filter, hidden Markov model, discrete Fourier Transform, and wavelets. These are the references. Thank you very much.